One second, let me try again. Yeah, I'm a little confused, okay, about where the file is, but let's just go directly to the class 2 nodes. All right. Can you see? Yeah, so continuing from last time, we will move towards capacitance. So last time, we talked about there's a relationship between E and V. Um, we kind of finished that part, and then we did some example calculation of some structures, and we did a bit of our problems. And today, in the first hour, we will talk about capacitance C, yeah, and the energy inside the capacitance U, yeah. And then we will add on number four. You see number four, analyze the effect of dielectric materials. So if you put dielectric or insulators inside a capacitor, how does that change all the parameters of a capacitor? So that's what we will cover in the first hour. So let's go to this part. Yeah, we did this already. It's Gauss. Okay. So it's a bit of review. Um, so let's look at, yeah, we had this diagram last time. Second, something is a bit, okay. Okay. So let's say last time we talked about if you have a charge, you start with the delta Q. And you can use E is k q over r squared with vector field to you can calculate the electric field from the charge. And the charge can be a line charge, could be a point charge, could be a surface charge, could be a volume charge. Yeah, and you just do you add up the vectors together and then you integrate and you get E. But also, we talk about we can actually have a bunch of charge, and then we go in this route to calculate the potential. So yeah, we use dV is k dq over r, and then integrate them. But this integration of the potential, it's you don't have to add them vectorially because it's scalar field. It's easier. Yeah. So you can have so from the charge you can calculate the potential. And there is um, there is a relationship between, or even a better definition of the potential where you calculate from E to get V using this formula, this line integral. Yeah. So Practically, there would be, it means that there are two ways to calculate the potential. So you do the V is KQ over R and then sum it up. And also you find E first, and then you integrate E to get a V. But you know that this method of V KQ over R, this formula doesn't work for infinite charge. Like an infinite plane, it would not work. An infinite line, this formula will not work because this formula have assumed that at infinity, the potential must be zero. But for the situation where the charge extend to infinity, at infinity there's still charge, so it cannot be zero. So this formula just fail. So we have to come back to the original definition of potential, which is it has a meaning of us like climbing like walking on a path in the field and see how we are climbing the mountain, or we climbing up the mountain or climbing down the mountain. Yeah. And let's say if if we know E, we know already that we can calculate V, right? But on the other hand, if we know V, we can also trace back. We take a derivative and you get E out of it. Yeah, through this formula. E is dV over dx with the negative sign in front. Okay, so to give an example, last time we did this calculation. So the first example is we look at a spherical shell of charge. So let's say you have a ball and the charge is on the surface like this. And we knew from Gauss's law that the electric field inside has to be zero and the outside will have to be KQ over R squared, like this picture. So from that information, we can write the electric field as a function of radius, something like this. So inside is zero and outside it drops as KQ over R squared. So it's the transition point, the change happens at R equals big R, the radius. And this value will be KQ over big R squared, a fixed constant. Now that we know E, we can use this formula to integrate to find the potential. So we just imagine we are walking from infinity towards the center of the sphere. And then we're going to keep measuring the potential. Yeah, so we do this integral, and then we would get this graph for V. So we know that outside the sphere, we are climbing. So the electric field, the red line is going outward. So as we're walking towards the center, we're walking against the field. So it's as if we are walking up the hill. So you're going to get this formula, KQ over R, for the potential in the region outside the spherical shell. But once you hit the shell, the surface of the shell, and then you continue to walk towards the middle, you know that there's no electric field there, so there's no resistance, nothing against you. So the potential change will be zero, right? So you get this kind of a flat plateau in the middle. And then you would have, in effect, this potential function as KQ over R, where R is the distance from the center for region outside. And for inside the shell, you get a constant KQ over big R. Okay, does it make sense? Yeah, it's a bit of review. Yeah, if it makes sense, can you click the like emoticon for me? Okay, thank you. And what's interesting, we can look at the second example, which is one infinite plate. Yeah, one infinite plane of charge. And the parameter, so this side, the parameter would be of this configuration would be charge over area, right? Sigma. And then we would continue the same process to write out the formula for electric field first. So electric field from Gauss's law, we would get a sigma over 2 epsilon naught. So you have this graph. Make sense? this graph here for electric field. Yeah, so it's positive in the plus z direction and negative constant in the minus z direction. And now you can imagine if you walk from infinity, you're gonna climb uphill. If you walk from the right plus infinity and walk towards the plane, you're gonna go uphill. And the slope will have to be constant, right? Because it's a constant electric field. And then if you continue walking across the plane towards the left direction, towards the negative z direction, you're going downhill. So it's going to look like this. Yeah, so that's the formula for Vz. It's going to look like this. Does it make sense? And if you look at it, you will realize that if you take a derivative of V, you get Ez. You take a derivative and then flip the sign, you're going to get exactly this. Yeah, so you see the integral and the derivative relationship between E and V. Does it make sense? And now, even more interesting is in a lot of devices, we use this plane of charge to make parallel plate capacitor. So you put a positive charge, positive plane, and negative plane together, separated by a distance d. And then you combine the field, you sum up the field, and then you realize that the field outside will be zero, and the in between will be E equals twice of sigma over 2 epsilon naught, which turns out to be sigma over epsilon naught. So when I plot the graph of E, I get this. Does it make sense? So it's zero outside. So from d over 2 and lower than minus d over 2 is going to be 0. And in between this region is going to be a negative value of minus sigma over E naught. Okay? Because it's to the left direction. And then if you think of it in terms of potential, it's going to be like this, right? Because the right side has a higher potential and the left side is going to be lower potential. And I know this potential difference would be the integral of E over the line, the direction, right? So delta V is going to be E times D. Yeah. And I know that E calculated from the charge density of the plane, it's going to be sigma over epsilon naught. So I have basically this formula for the potential difference of the parallel plate. Makes sense? So the situation, so it means that if we look at the definition of capacitance, what is capacitance? So you can look at this image. Okay, so capacitance is defined by this phenomena. So you have a plane of two electrodes, and you start to take charge from the positive charge from the left side to the right side. So you're gonna continuously building this charge difference minus Q and plus Q over some time. So you build the charge first, and then the charge create electric field. So you get from Q, you get E. And then from E, once you have the electric field, then you're going to build up some potential difference. So as you do line integral from positive electrode to the negative electrode, you're going to get this delta V. Does it make sense? So the logic goes like this. So you start with Q, and then you build the E, and the E creates a potential difference between the two conductors, delta V. And you always have this relationship, this linear relationship between the charge that you build up and the potential difference. So Q will be proportional to delta V. And so you will define the capacitance as Q over delta V. So C is defined as capacitance. Capacitance of the conductor. Okay, does it make sense? Yeah. So the more capacitance means Q equals CV, right? So the higher capacitance, meaning from the same voltage, you get higher Q. Does it make sense? Yeah. So if you look back at this formula for potential difference for the parallel plate capacitor, you will realize I can write sigma as Q over A, right? And I divided Q by V, so I get the parallel plate capacitance. So I get that the C parallel plate would be epsilon naught A over D, this formula. This is something you should memorize. Yeah, should remember and check how it makes sense. Yeah. How does it make sense? So if you have a larger area, it will have higher capacity. If A increase, C increase. Why? You have to make intuition about it. So when you have a larger area, you have more area to put the charge in, so you have more capacity. But if you want to increase the capacity, what do you do with the separation D? You increase or decrease D. If you want to increase the capacitance. If I want to increase C, I have to decrease D. Make sense? So you make the plate closer together, so the attraction is more. Then you can you can keep more charge. Does it make sense? So in general, the capacitance of a conductor depends on its shape. You see, A and D are geometrical parameters. And if you have different shape of the capacitor, say you have two concentric sphere, let's say something like this, then you're going to have a different formula for C, right? You can have, it's going to depend on the radius A and the radius B of the capacitor. Does it make sense? Yeah, and if you look at this sheet, it's going to give the formula for concentric sphere capacitor. Yeah. And if you look at the formula for concentric sphere capacitor, I think it's something like concentric sphere. It's going to be epsilon AB over B minus A, something like that. I think, if I remember correctly. I'm not sure. The unit makes sense, right? Yeah, unit makes sense. And if I make the radius B very large, okay? If I make the B very large, much larger than A, it would just be epsilon naught A. Make sense? So it means that if I have just one sphere with radius A, the capacitance for the sphere will be as if the above formula, but take the limit as B go to infinity. So it's going to be epsilon naught A. Make sense? So the larger radius, the larger capacitance. Okay. Does it make sense? So if it makes sense, can you click the like uh, icon? Okay. Now let's look at, thank you. Now let's look at some of these questions. Let's see. Let's look at question number 9. So the situation is you have two metal sphere. They are connected by a wire with a switch in the middle. Initially, the switch is open, and sphere 1 has a larger radius and a positive charge. Sphere 2 has a smaller radius and is originally neutral. And then you close the switch. So afterward, sphere 1 will have charge Q and add potential V1. And then the field will be E1. Whereas sphere 2 will become Q2, V2, and E2. So this is before. And after, it becomes like this. So it's going to be some charge here. Something is wrong with my pen. Okay, now it's back. So we're gonna have some charge here, right? And you're gonna get Q1 and then E1 and then V1. And here it's gonna have Q2 and then E2 and then also V2. So I want to compare which one has a larger V and which one has a larger Q and which one has a larger E. So yeah, can you type uh, for part A first? So when you connect them together, yeah, what happened? Let's say we have this formula. We have Q equals CV, right? And we have also the energy. We're not going to use the energy. I don't think we need the energy here. So the energy, uh, potential energy inside the charge capacitor would be 1/2 QV, which is equal to 1/2 CV square or 1/2 Q square over C. Yeah. So we have two formulas to use. Okay, please type in the chat what you think about the potential. Is V1 larger than, smaller than, or equal to V2? Give you 1 minute. Or if you like, you can also say it in your mic in your microphone. I give a little hint. So there's V, the Q, and E. One of them has to be equal in order for the system to be in equilibrium. Which one will become equal? Q, V, or E? Any idea? Just guess. So what will happen is the charge will flow from the sphere 1 to sphere 2, okay? Until it will stop flowing when V1 equals to V2. That is the solution. Why? So it will flow until V1 equal to 2. That's the point where the potential is the same. So it's the same level, like a plateau, So the surface of the sphere on the left and the right will have an equal potential. So there's not going to be any flow further, right? Yeah. Makes sense. So when Q change, the potential of the surfaces, the sphere will change. So as the Q flow, V2 will get bigger and V1 will drop. At the beginning, this V2 will be zero. So this is before, and V1 is quite high, and V2 is zero. And now, as you connect them, uh, Q will increase, Q2 will increase, Q1 will drop up to the point where V becomes equal. Yeah. And now, okay, how do we find Q and E1? Which one is larger? Which one has higher capacitance? So, okay, you can do it this way. So when you have Q1, the electric field E1 will be KQ over R1. And E2 will be this would be Q1, KQ2 over R2, right? And from E, you can find V, right? V will be this will be R1 squared and R2 squared. And V will be KQ1 over R1. And V2 will be KQ2 over R2. And because we know that R1 is larger than R2, right? So, and these two must be equal, right? So, no charge flow anymore. Okay. So it means that Q1 over R1 must be equal to Q2 over R2. And because R1 is larger than R2, so Q1 must be, so it means Q proportional to R, right? So it means that Q1 must be larger than Q2. So Q1 must be, this is equal, this is larger, and E1 will also be, what is it? So this is equal to V1 divided by R1. And this will be V2 divided by R2, right? So we know that because V is the same, so E is inverse proportional to R. So therefore, we say E1 must be, so because R1 is larger than R2, E1 must be less than E2. So this would be smaller than E2. Does it make sense? Okay, I let you look at this for 20 seconds. Does it make sense? If it makes sense, can you click the like button? Okay, so that was one way of solving this. And if you look at the second formula, you realize that you can look at this as a capacitance problem. So you see that Q is proportional to voltage, right? And this voltage would be the difference between the voltage on the sphere and infinity and the ground, okay? Right? You can take infinity as ground. Okay. So what is C then? Q is CV, right? So C is Q over V. So Q over V would be R over K, which would be, what is it? K is 1 over 4 pi epsilon naught. So 4 pi epsilon naught R. That is a formula for sphere. Okay, so my formula I gave you earlier was not correct by a factor. It needs 4 pi. Okay, so let's go back and fix it. Okay, let's go again. Yeah, let's go back to your note if you have written down and fix that to the correct formula. See, it's here. Yeah, so this has to be 4 pi. 4 pi. And this would be 4 pi. Okay, in order to it to be correct. Yeah. Now let's go to our problem again. Now I fixed it. Okay. Now then you see clearly that C1 must be because R1 is bigger than R2, then C1 is also bigger than C2, which makes perfect sense, right? Bigger sphere would have bigger capacitance. And once we know that we have more capacitance, we have this formula Q equals CV. So because V has to be the same, so if C is large, Q has to be large. Does it make sense? So because we say that because C1 equal than C2, then Q1 must be larger than Q2. So we can also use this to get the answer for questions B and C. Make sense? So because Q1 larger than Q2, then uh, we have E is proportional to Q over R. So then we have E1 over E2 will be Q1 over Q2 divided by R1 over R2. And we know that Q1 over Q2 will be, will be R squared, right? Sorry, I was like, forget the formula. So this has to be this. Then ratio-wise, Q1 over Q2 will be R1 over R2, right? So in the end, will be R2 over R1. So then we have, because R2 less than R1, then we have E1 less than E2, just as our answer before. So this is an alternative way to solve this problem. One must be less than E2. That's the solution. Okay, we have the solution, and we have V1 must be equal to V2. Yeah. Is it clear? If this is clear, can you click like? Okay. Now let's look at some problems about capacitor. Let me open a new note. It's EM class 3. So let's see. Where is that? Class 3. All right. Okay, now I found it. So let's see. Here we go. So this chapter will be about circuit, will be current resistance circuit, and there's a question on um, capacitance and dielectric. So question number 8, let's look at that. There are two sub-questions, two quite different situations. So let's see the first one. We have 2 by 2 centimeters electrodes with spaced 1 millimeter apart and with a wire to 9-volt battery. So let's draw this situation to make sure we understand what it looks like. So let's say we have a battery. Let's wait a moment. It frozen. Okay, here we go. So we have a battery like this, 9-volt, and we have a capacitance. We have something like this. Okay. And area is 2 by 2 centimeters square. And the spacing is 1 millimeter. Okay, so question A asks for the charge on electrode and the potential difference between them. So delta V. Okay. And then the wire got disconnected. So this is before and there's an after. An after look like this. Oh, I draw terribly. So let's try again. So still 9-volt and it gets disconnected. So it becomes like this. Let's say. And insulated handles are used to pull the plate apart to a new spacing of 2 millimeters. So I increase this. Yeah, so this become 2 millimeter. Okay, so it increases. Now what is the charge? So maybe I call Q1 and Q2 maybe. So I call this D1 and D2. And before it's gonna be Q1 and V1, right? It's gonna be Q2, V2. And what might change? What else might change when you change the D? C1, right? And C2. Okay, let's look at this. So, okay, let's first do some calculation. What is Q1 and what is V1? Okay, anybody know? So, what do we know? We know the voltage, and with this A and D, we know what do we know? We know C, right? So C will be epsilon naught A over D. Okay, so it's some number. It's gonna be 8 times 3 to the negative 12 times A, which is 4, 10 to the negative 4, right? Centimeter square, and 1 millimeter. So it's 1 times 10 to the negative 3. Yeah, that's a number. So Q equals CV. So first thing I know is that I know C and I know V. What is V1? V1 must be 9-volt, right? And Q1 is gonna be C1 V1. So it's gonna be this number. So 8.33 times 4 times 10 to uh -4 plus 3 becomes -1 uh and -1, so it's -13. Yeah. Okay, farad times, sorry, and times V, which is 9. So times 9. So the unit is going to be coulomb. Yeah. Now, so after the wire disconnected and pull apart, what would it be? Some number right here. Some number here. Okay, so what's going to change? This is important. So after you pull them apart, C is going to change, right? Because D will increase. So D will increase. Wait, what happened? Yeah, D will increase. So C will drop. C equals epsilon naught A over D. So because D increase, C is gonna be half, right? And what happened? So C2 is gonna be half of C1. And after disconnected, does V change or does Q change? So once you charge it, okay? So once you charge it, you're gonna get some charges on this, and then you disconnect. Now charge is gonna be the same, okay? So what's gonna be the same is the charge, and C is gonna drop, and V is gonna increase. So Y. So it's like you have Q equals CV, right? So C is gonna drop, Q is the same. C is gonna drop, and to keep Q the same, V must be increased. Does it make sense? Yeah. So Q2 is gonna be the same as Q1, but V is gonna be twice of V1. So it's gonna become 18 volt. Make sense? Yeah. So that's the answer. So you're gonna put in the number, if you plug in the number, you get the answer. Does it make sense? So this and this. And then we're gonna get right down. So V2 will be 18 volt and Q2 will be equals to Q1. Okay, let's do the last question for now, 55. So the situation is the same, except so number A will be the same, right? So I'm gonna write V1 will be 9 volt. Q1 will be this one, 8.33 times 9 times 4 times 10 to the negative 13 coulomb. And okay, the situation now is different. While the plates are still connected to the battery, you pull them apart to a new spacing of 2 millimeters. So the picture looks like this. So you're gonna go from the original one like this, and then you make it to like this. So you still keep it connected. And then you increase D. So D2 is gonna be 2 millimeter, but still connected to 9 volt. So now let's look back at this formula again. Q equals CV. So in this situation, what changed and what remained the same? Is V gonna change or Q gonna change? So now you know that because we increased D. Yeah, someone say something. A, what do you mean A change? So C gonna drop, right? It's gonna be less. Yeah. What is the same and what change?
V is the same. Q change,
Yes, that's correct. So V is the same and Q, what is Q? Is Q gonna increase or decrease?
decrease,
Decrease. Yeah, because Q is proportional to C. So now Q is gonna be, what is it? It's gonna be half of than before, right? So so V2 is gonna be the same 9 volt, but Q2 is gonna be half of Q1. Make sense? Because it's less capacitance and the charge gonna flow back into the battery. Is that clear? So, all right, the final point is if you add a dielectric into the capacitor. So let's say you have a situation, you have to think of a situation, a very concrete situation. Let's say you have this kind of capacitor, some V, and then maybe you disconnect it first to keep the Q the same, right? And then you add some dielectric in the middle. So let's say here, and then I add some dielectric. Let's say this is dielectric. Let's say it has a dielectric constant K. So K is a dielectric constant. Dielectric constant. Then the question becomes, what's going to happen to Q, to V, and to C? And maybe also E inside the material. Of course, it depends on whether you connected it to the voltage or you disconnected. Yeah. And what's going to happen in dielectric is that the charge that is already there uh, on the capacitor, let's say here, plus Q and minus Q, it's gonna induce the polarization inside the insulating material. Okay. And it's gonna change the electric field. It's gonna change. In this case, Q is gonna be the same. And the electric field is gonna drop. And the voltage is gonna, yeah, what happened to C and to V in this case? Yeah. So yeah, because now it's already 2, so I asked you this question. Please figure out, and we'll talk about this next time. Okay, for this part. How does it change C? How does it change V? How does it change Q? How does it change the electric field inside? Okay. Um, let's take a little break. Maybe now it's 5. Yeah, maybe like a 7 minute or something, just to stretch and go to a toilet. Yeah. And yeah, let's do that. Maybe I leave you in the small room and you can chat with each other uh a little bit about what were the main points that you get from this 1 hour class and the key idea and what is challenging, what is difficult for you, what do you need to review. Okay, so I'm gonna open some breakout room for you. Group of 3 or 4. Let's do that. Options. Okay, 5 minutes. Yeah, let's take a break. Hey, welcome back, everyone. Yeah, if you're back, can you click heart or like? Hmm. Okay, can you hear me? Is everyone back from the break? Okay, so let me share with you some uh sheet about circuit. Yeah, so you can take a look. I think I should move on to internet. I think this hour I should move on to magnetic field so you have time. Uh, it's a bit more involved topic. So let's see. Oh, internet cuts again. All right. Can you guys still hear me? I think it was off a little bit. If you can hear me, can you click like, please? Okay, thank you. Okay, so let's see. Let me share with you the screen. Okay, so if you go under the old lecture notes, the electric current sheets, there will be this note, RC circuit and resistor circuits. Okay, it's loading. So I'm gonna walk you through. Uh, so the main idea about circuit theory is that there are you have three concepts that you need to solve any problem. Okay. One is the current in for any junction, sometimes we call it vertices. Like here, for example, there will be one in and two out. So all the in current is gonna be equal to the sum uh of the out current. It's called KCL, Kirchhoff circuit law. So current in equals current out. That's one concept. The second concept is that when you go through a loop, let's say I walk from this point down and then up the battery and then through a resistor, I complete a loop. And when you complete a loop, the voltage will keep dropping across different elements and then it comes to zero. Yeah. So this is called Kirchhoff voltage law. Okay. So it just means that VR1 plus VR2 is going to be equal to the potential E. Make sense? Yeah. So it's a voltage difference across a loop. It's going to be zero. And the third information you need to know is the relationship between current and voltage across each element. Yeah. So yeah, it's called VI relationship between each element. So you know that for resistance, V2 is going to be I2 R2. Makes sense, this term. And V1 is going to be I1 R1. Yeah, and the V across the voltage across the battery would be E. Makes sense? So you need three concepts to write out the equations for any circuit. And for example, in this issue, in this example, you have a battery, two resistors, and one capacitor, and you have two loops, and you're gonna write out all the equations. So and then you would have unknowns, right? So the number of unknowns, you need the same number of equation as the number of unknowns to be able to solve for all the unknowns. Make sense? Yeah. So let's say in this case, I have yeah, this is a bit complicated. You have I1, I2, and IC. You have three unknowns for the current. And when I switch, and when I turn the switch, I close the switch, the voltage across this is gonna be different. R1 and R2 will change in time, right? So and then it's gonna charge a capacitor C. So it's a bit complicated. And you have this relationship between I and V for the capacitor here. So you have Q equals CV, right? And then you also have the relationship between Q and IC. So this is a bit complicated. You actually have 1, 2, 3, 4, and 5. Is that right? No, sorry, 1, 2, 3, 4, 4 equations. Makes sense? So you have two loops, one one junction, and one relationship between IC and Q. So you have four equations, differential equations, four unknowns, and then you can solve for it. Yeah, that's the idea. Okay, it shows how to solve it and things like that. Makes sense? Yeah. So overall, whenever you have an RC circuit, and then you turn the switch, the close switch like this, it's gonna charge the capacitor, right? It's called charging. And let's say if it's already charged and then you open the switch again, it's gonna discharge. C is gonna discharge into R2, right? So there's a process of charging and discharging. And whatever system you solve, you're gonna get this kind of graph. So the capacitor, it's gonna have like a zero voltage and they're gonna increase into a constant. Make sense? And the chart's gonna have the same graph. Yeah. So you're gonna have this term appearing in the solution. So something like e to the negative t over tau, where tau is a constant. Okay, tau is some constant that is made up of R and C, right? Yeah, so my tau here is gonna be complicated because R are in parallel. So you're gonna get something like this, RC. Yeah. Yeah, so this term, it signifies the exponential decrease and reaching some equilibrium value. Yeah, so if you look at I, it's going to look like this also, like a exponential decrease, something like that, a combination. Okay, so that's RC circuit. And you can use the same three principles, three concepts to solve for any DC circuits. Yeah, so you're gonna have a KCL, KVL, and the relation between I and R for each element, each circuit element. Yeah, and this sheet is going to show you different ways to solve this kind of circuit problem. Yeah, in the end, you would need uh, the number of equations, at least the same number as the number of unknowns that you don't know in the problem to solve the problem effectively. Okay. So yeah, that's it for the circuit. Anybody has any question, I would recommend you go and take a look at this sheet to get a clear understanding, better understanding. And now, I guess if nobody say anything, we can move on to magnetic field, class 4. So we're gonna cover about Biot-Savart law. It's a procedure to calculate magnetic field from current distributions. It's equivalent to Coulomb's law, okay? But it's a bit more complicated because it involves right-hand rule and uh, cross product, okay? And you still have to do the integration and everything. And the second point is about Ampere's law. Ampere's law is similar to Gauss's law, yeah. And the last one we'll talk about the magnetic force F equals QV cross B. Let me look for the sheet I draw yesterday. I found it. Okay, here we go. So let's take a look at the formula, the summary of the formula for this part. Okay. So yeah, the first hour we talk about capacitance. We have all this formula, and we talk about RC and dielectrics. I ask you to go review yourself, and then we will talk about that next time. And now we talk about Biot-Savart law and Ampere's law. So the idea of Biot-Savart is that when you have a current carrying wire, you have a current element IDL. Yeah. And then you gonna have this formula. So dB equals to mu naught over 4 pi IDL cross R hat over R squared. This is Biot-Savart. And you call it IDL as a current, a small current element. And the vector R, you're gonna cross product it. Yeah, and the vector R hat is measured from the source, the current element, to the point of interest. Yeah, so it's gonna be a function of the source coordinate. So if you have many different pieces and you have to add together through integration, there would be a parameter from the position of the current element in it, and then you would do integration, similar to Coulomb law. And you have to add them up vectorially as well. That's the challenging part. You have to think in 3D, yeah, and use the right-hand rule. On the other hand, so the main shape that you want to be able to calculate electromagnetic field would be a straight wire, which can be finite or infinite. And another example is a circular arc. Yeah, and when you complete a circular arc, you have a loop. And then you can actually calculate the magnetic field at the center of the loop using Biot-Savart law. And let's move on to Ampere's law. So you have this formula of Ampere's law. So you have magnetic field B dot dl and integral over a loop equals to mu naught I through. Okay, and mu naught is 4 pi times 10 to the negative 7. So you'll see that it's quite similar to Gauss's law, but it's actually a bit different. So for Gauss's law, you have the charge that is enclosed in the surface, in a closed surface, and then it generates electric field. And the left-hand side of the Gauss's law is actually the flux of the electric field through the surface. Yeah, through the closed surface. So dA is actually the closed surface. Okay, but the left-hand side of Ampere's law is actually a line integral. So Gauss's law is a surface integral, but Ampere's law is a line integral. That's the main difference. This is a surface integral. Okay, this is a line integral. And if you notice the current is going to be current through this loop. So yeah, so you have a surface, and whereas this you have a line with some direction. Okay. So when you close the loop, then you have some kind of surface. So to give a concrete example, let's say you have, look at the above this picture. So the current I is a wire, it's a straight wire, and it's pointing out from the paper to your face. Okay. And then this purple current I is gonna make a magnetic field. So you're gonna use your right hand. So let's do it with me. You point the thumb of the right hand along the wire, the purple direction, so out of the page. And then your four fingers are gonna curl in the direction of the magnetic field, the green line B, right? So I, the purple, create the green B going around. And let's say, so originally it's gonna look like this. Let me draw it explicitly. So I have the current, and then it's gonna generate this field. Let me draw again. It's gonna generate this field, this field, this field B. And now let's say I pick a loop, closed loop. So maybe I pick at some radius here, this the inner radius. So like this. And let's say I pick the direction of the loop, the same direction as B, just for simplicity. So I'm gonna have this as DL, right? And now if I integrate B along DL, it's gonna be a positive number, okay? And if you notice, this loop is also gonna make an area, right? A cross-section area that's a circle, where the eye is gonna be pinching or going through outward, yeah, to out of the page. Yeah, so that's what it means by eye through. Yeah, it's gonna pinch through the closed surface. Make sense? Yeah, so for infinite wire, it's gonna make things a lot easier. So you're gonna get something like this. So B, the field B, uh, dot dl, and over the loop is gonna be mu naught I through. So if it's an infinite wire, I'm gonna get I and mu naught gonna be equal to B times 2 pi r, right? It's gonna be 2 pi r. Now I'm gonna get the formula, an easy formula for B of infinite y. So it's gonna be mu naught I over 2 pi r. Super easy. Yeah. So Ampere's law can be used a bit like Gauss's law for highly symmetric situation. Yeah, that's the formula for infinite straight wire. So mu naught I over 2 pi r. Okay, so the further away from the wire, you get less magnetic field. Does it make sense? And another two, so let's say another two situations where you can use Ampere's law very easily would be a plane of current. So what is a plane of current? Let's look at this image. So a plane of current is you have wire with current I, and they stack in a plane. Yeah, maybe you can think of like a sheet of paper with a current coming through out of the page. So on the side view, it's going to look like this on the right hand side. And what does the field look like? The magnetic field. So you're going to have this field like a B, right? In this way, it's going to go below, it's going to the right, going to be to the right, and above is going to be to the left. And let's say this Y are super, this plane are like infinitely long, right? So in the end, you're going to have just below is going to go to the right, and above is going to go to the left. If you look at it, okay, so okay, now do I quantify this current? So let's say I would have n amount of current I over the length L. And I call this surface current density. It's a bit like surface charge density, but this is a surface current density. Does it make sense? Yeah, so the number is infinite and L is actually infinite. But when you take a ratio, it's a constant. Um, yeah, and let's say I'm gonna use the Ampere's law to calculate the magnetic field. So what I'm gonna do is I'm gonna pick a square, not a square, sorry, a rectangle. This pink box, uh, this pink loop, not a box. Yeah, and I give the same direction as B, and I'm gonna do line integral of B along this thing, and then I'm gonna be able to solve for the magnetic field of a plane. If you look at it, it's a bit similar to the plane of charge, but this is a plane of current. But the vector, the direction of the magnetic field is going to be different from electric field. Okay, it's going to be parallel to the plane, not out of the plane. Okay, and an interesting case is a third situation is when you wrap this infinite plane into a solenoid. So let me show you this. So let's say you have this plane and the current is coming out like this, go like this. And then if I wrap this plane into like this, then I have a solenoid, right? Like this. So I'm gonna have this current going through like as my right hand like this. Yeah. And then my thumb is gonna go this way. It means that there will be magnetic field confined inside this limited region in this direction. So you get a uniform magnetic field confined within a nice area, right? So in magnetic term, this is kind of equivalent to the parallel plate capacitor, where we make a uniform electric field inside a closed area. But this is you're gonna get a magnetic field, uniform magnetic field inside a closed area. Yeah. So this is called solenoid. And you can make like even a fancier one, very useful structure is you wrap this around and make like a donut. It's called toroidal magnetic field. Yeah, again, you're gonna get a similar expression for the magnetic field in its case. So yeah, so I encourage you to look in this sheet here. Let's see. In my old lecture notes to see how you calculate this kind of thing. So magnetic field and magnetic force. This one. Note 5, B field. Okay. Yeah, so I do the Biot-Savart calculation in the first part, and I also do the formula for using Ampere's law. So we just did this, and infinite sheet of current like this, or a solenoid like this. Okay. Okay, let's look at more example of Biot-Savart. So I think it's here. Yeah, let's look at Biot-Savart how you do the calculation. I have about 15 minutes left. Okay, here we go. Actually, let's go to the first one. This make it easy. Okay, this is Biot-Savart formula. And the way you have this wire with some current I, and you're gonna have IDL. So this is gonna be your IDL. And then let's say I am interested in the field at this point P. So what I'm gonna do is gonna draw a line, a vector from the source to the point. So it's gonna be this vector R. And then the R1 unit is this small one, this small thing. And what I'm going to do is I'm going to use right hand rule. So let's try together with me with your right hand. So put your right hand, put the index finger along IDL, and then you're gonna rotate around that index finger to face your palm to the direction of R, sorry. Yeah. And now you're gonna see that your thumb is gonna point into the page. So you're gonna have DB into the page, this direction. Does it make sense? Another way to check it easily is you know that when you have IDL and R, you cross the two. When you have IDL and R, you're gonna make a plane, and this plane happens to be the plane of the screen right now. So DB has to be perpendicular to this plane. So it can either be out or into the page. And in this case, if you cross from IDL towards R, you're gonna go into the page. Does it make sense? Yeah. So you can actually use this to find the formula for the straight wire. Yeah, like this, for example. So you have a straight wire. I do IDL cross R. So I'm gonna get DB inside into the page as well. So um, let's say if my current like this will be my IDL. And cross R, I'm gonna get B into DP into the page. Yeah. And now if I pick a different, let's say I pick a different piece, different element. So let's say I pick this one here. Pick this piece here. Now what's gonna be different is my R is gonna be this R. Okay, gonna be this R. So it's gonna be shorter. And my source coordinate is gonna be Y. So this is gonna be my Y. And so I'm gonna have my R. Let's say my R here is gonna be x squared plus y squared. Square root. Yeah, and my angle is gonna be a function of y as well, right? So so I'm gonna add them up vectorially. So we're actually quite lucky because for any pieces, any y, dB is in the same direction. So you don't have, yeah. So you don't have to decompose the vector. You just add them up. Yeah, you can then you're gonna have to do some integral with dl is dy. Practically, you do the integral and you get the answer. Does it make sense? So yeah, let's scroll down a little bit to see another example. So let's say you have a circular arc of wire. Yeah. And let's say the process you're gonna do to do the integral is you break down this little piece, dl. So I have this I dl. Okay, and my R, I'm gonna measure it from the source to the point of interest. So let's say I want to know about this point here, what the magnetic field look like. So I'm gonna do this vector R. Okay, it's gonna be my R. So I do put the right hand, you get your index finger, IDL. So it's gonna go northeast, and then you point your palms towards R, which is the west north, right? Northwest. And then you cross it. Yeah, now your thumb's gonna point out of the page. So this is gonna be your dB out of the page. And you notice that IDL always perpendicular to R, so it's makes your life a lot easier in this case. So yeah, so you're gonna get like B equals mu naught over 4 pi. This R is gonna be constant, big R. Okay, and d theta over R squared. So in the end, you're gonna get this formula that the magnetic field is gonna be mu naught I theta over 4 pi big R. And theta is just the angle of the arc. So let's say if you have a full arc, if you have not a full arc, I mean like a full round, so theta will be 2 pi. So if you have a full loop, a complete loop, your formula is gonna be mu naught I times 2 pi over 4 pi r, which in the end you're gonna get mu naught I over 2r. That's for a loop shape. Make sense? So now if we come back to the sheet that I showed you a bit earlier, this one, a summary of how you calculate this kind of thing. Here. So you have a line of current and you do the integral. And let's say if the line is finite, you're gonna have some of these terms, sine theta r plus sine theta l. Yeah, I encourage you to take a look at that. And if you have an infinite line, you can take a limit where the thetas are 90 degree. And then you would get this B field of an infinite line of current, which exactly match our previous calculation through the Ampere's law. So it's 2 pi r, the circumference of a circle. Yeah. And let's say if you have a current loop and you go to a more general case of any point along the axis of the loop with some distance z, for example, then you will use the right-hand rule again and calculate dB and add them up vectorially, and then you would get this formula. And when z equals to 0, you're gonna get what we had before. at the center of a loop. Yeah, and with this technique of a straight line or a curved line through Biot-Savart law, you can construct a more complex circumstances. For example, you have a square loop and you want to find the magnetic field right in the middle. So you plug in the formula and you can calculate the magnetic field at the center. Does it make sense? Yeah, and these are all the calculation that I uh, demonstrated for you in this sheet. Okay, the last point, the third point about magnetic field that we'll cover this week is uh, the magnetic force. So as opposed to the Coulomb force, Fe equals QE, the magnetic force is, you only experience magnetic force when there's a moving charge going through the magnetic field. Okay, so when we say FB equals QV cross B, B is from the field and V is the test charge moving. Yeah, and the moving charge could be the charge inside a current. So this would become IDL cross B. So you know that the force will always be perpendicular to the current and perpendicular to the magnetic field. So it has a 3D characteristic. Okay, now an interesting case is if you have current going through the same direction, what kind of force do they experience? So if you think of them as charges, they're gonna repel, right, through the electric field. But if you look at its magnetic property, what's gonna happen is that you can think of um, charge, you can think of current one acting some force on current two through magnetic force. So the process goes like this. So you have I1, and I1, you use your right hand rule to point your thumb, you grab around this wire. So your thumb points upward. And on the left area, you're gonna get the magnetic field pointing out of the page. And on the right side, you're gonna get magnetic field pinching into the page. So I1 generate B1 first, which depends on the distance from the wire. Okay, it drops with distance from the wire as 1 over R. And now, as the charge in I2 is moving against this B1 field, so I2 is moving in B1 field, then it's going to experience the magnetic force. So QV cross B. So my QV is I2L2, and it's going to cross B1. So I'm going to have a force on current 2 due to current 1, okay? So this is going to be F1 on 2, and it's going to be in the leftward direction. You do the cross product. You take your right hand again, and you go along I2, which is you put your index finger uh, upward, up along I2, and then you're going to turn the palm facing to B1, okay? Right? So what is B1? B1 goes into the page. So you turn the palm into the page. Yeah, and now your force is your thumb. So the force is gonna be leftward. So you're gonna get attractive force when you have current in the same direction. Does it make sense? So now you have this formula for the current carrying wires with current in the same direction. It's gonna get attractive force with this formula from F1 to F2. Yeah, if it makes sense, can you click a like sign? Okay, now let's do the last, I mean, maybe I might have to go over time a bit, maybe 10 minutes. Let's do a bit of problems. So let's see where I can find it. Okay. So let's go to class 4 and to look at the pretest magnetic field and force. Yeah, so yeah, let's do the first 2 questions. And yeah, as a homework, you can try the other questions in this one. It's all about Biot-Savart and um, Ampere's law and FQV cross B. Yeah, please do a lot of practice in this. It's gonna help you. So let's do the first 2 questions. Um, I think I have written it here as well. Let's see. Yeah, let's look at the first question. Yeah, I did this already yesterday. Let's see. How should I share with you this one? Oops. Okay. All right. So let's look at the first question. So you have a wire with current I from the left and goes toward the junction. And what is the magnetic field at the dot, the point of the dot? So the first stage you have to think about is when current I coming from the left to this junction, what's going to happen when it hits the junction? So you have 2 output here, right? So it's going to go up and down. And the sum has to be the same as it comes in. So it's going to split into I over 2 and I over 2. Yeah. Top part's going to go up. The bottom part's going to go down. And now basically you have 3 sections of wire. Makes sense? And now I want to find the magnetic field at this point, P. How do I do that? So I need to combine 3 contributions of magnetic field. So let's say the first part from the left side. So what I'm going to do is I'm going to think of a piece here. This is going to be my I1DL1. Okay, so it's going to be my I1, me IDL1. Okay, and now I'm going to measure the distance. So I'm going to do this one. It's going to be my R1. Okay, and I noticed that. So my formula for Biot-Savart is dB equals to mu naught over 4 pi I dl cross R hat over R squared. Okay. Now I look at IDL and R1. So my IDL is to the right and R1 is also to the right. What is the cross product? It's going to be 0, right? Because it's in the same direction. So I have my dB1 is going to be 0. So I'm not going to have any magnetic field from the left section. Okay. Now, if I look at this section instead, yeah, this is going to be my IDL2, I2DL2. Okay. And now my R2 is going to be this vector, right? Okay, so I'm gonna cross product them. So I'm gonna put uh my index finger up, and then I face my palm towards R2. Now my DB2 is gonna be into my thumb is gonna be into the page. So this is gonna be my DB2. Okay. So so it's gonna be some number. Then I have to integrate along half of it's like half. It's called semi-infinite. No, it's half infinitely long. Okay, it's gonna be my B2. Okay. Now, if I would do DB3, so I'm gonna pick this part. Okay. And let's say I pick this part. And then I'm gonna draw R3 from the source to the point of interest. This is gonna be my R3. Okay. So what direction is DB3? So I use my index finger down, and then I face my palm to in the direction of R3. And then my thumb, which is the result DB3 is gonna be out of the page. So I notice that DB3 and DB2 is gonna be opposite direction. And because it's the same length, right? I'm gonna integrate from uh the nearest one to infinity. So it means that they're gonna be equal, but opposite direction. So the total magnetic field for this case is gonna be 0. Okay, right? So I can say the magnetic field at the dot is gonna be 0 for this situation. Does it make sense? If it makes sense, please click the like button. Okay, thank you. So maybe we can move on to question number 2. Okay. Let's say I'm gonna start over again, everything. So the question goes like this. So you have current at this position. So 1, right? 10 ampere out of the page. And you have another line current, 10 ampere into the page. Yeah, at the lower position. Now we want to know the magnetic field at point A, B, and C. So how do we do that? Of course, we're gonna use some kind of Biot-Savart law for a long wire. So let's look at B first because it's in the middle. It's a bit easier, possibly. So first, we know that for infinite line, the B of the infinite line is gonna be this formula. We need to know this. We can use this formula. Okay. So it's gonna be mu naught I over 2 pi r. And at point B, what direction should it be? So I'm gonna do, yeah, so let's say this is my I1. This is my I2. Okay. And my vector R1, so at point B, I draw R1 from I1, something like this, right? I'm gonna use right-hand rule to figure out BI, okay? BI, what BI is it? So I'm gonna use my index finger out of the page, okay? Just do it together. Your right hand, your index finger out of the page, and you're gonna turn your palm towards the direction of R1. So your palm's gonna face down, okay? So index out the page, palm face down. Which direction is your thumb? Yeah. So you have a plane. Yeah, you create a plane between I and R, I1 and R1, perpendicular, right? So it's gonna be right. Yeah, your B1 is gonna be right hand side. This is my B1, okay? Makes sense? Now I'm gonna look at B2 from I2, and I'm gonna add that up with B1 and see what is the resulting the net magnetic field. So I2 is out. R2 is going to be from the source to the point B. So this is going to be my R2. Okay, and I use my right hand again. I2 is into the page. My index go to the page. and then you turn the face R2, which is up, then what direction is your B2? Where is your thumb pointing? It's gonna go to the right. So this would be my B2. And you know this the same magnitude, right? So I know that my net magnetic field is gonna be twice of B1. This is my net magnetic field. Okay. So I have this from the picture. I get this B net is gonna be 2B1. So at point B, my B is gonna be my magnetic field is gonna be twice of mu naught I over 2 pi R. And I plug in the number. Mu naught is 4 pi 10 to the negative 7, and I is 10 ampere, and my R is basically 1 centimeter, right? From the picture. So that's my R. And I just plug in the number and I get easily just 4 10 to negative 4 Tesla to the right. To the right. Or you can say plus X direction. Make sense? Okay, if this makes sense, can you click like button? Okay, thank you. Okay, now we can try to calculate the magnetic field at point C and A. And we kind of know that it should be a bit smaller because it's a bit further away from the source, right? But let's try it practically. So let's say I want to find B1 again at point A. So I'm gonna draw, oh, sorry. I'm gonna draw R1 this way. It's gonna be my R1 now. And then what direction is gonna be B1? Okay, right hand rule again. So index finger out of the page, you turn your palm to towards R1, which is gonna be southwest, right? Southwest. And which direction is gonna be your thumb or B1? So it's gonna be perpendicular to R1, right? And perpendicular to I1 at the same time, it's gonna be this vector. This is gonna be my B1. Make sense? It's perpendicular. And it's gonna be exactly 45 degree from the x-axis. Does it make sense? Because the position of I1 is 1, 1, right? So this is gonna be, this R1 is gonna be 45 degree. So B1 is gonna be also 45 degree. Make sense? Now I can do the same for B2. So if I draw from the below one, it's going to be my R2, which is aligned with B1 just exactly because it's 45 degree. And now my B2 is also going to be 45 degree. Makes sense? So you do I2 cross R2, I2 into the page and cross and turn your palm to R2 and then cross with I2, you're going to get this is my B2. Okay. And now, overall, my sigma B, my sum of B is going to be this one. Make sense? So I have to, project B1 and B2 on the x-axis, and the y-axis will cancel out. So basically at point A, my BA is gonna be 2B1 cosine 45 degree. And now I have to be careful because my B1, my R1 is different than before. It's further, it's longer, right? So I have this triangle. See, how do I draw it? So I have this triangle and I have this one. So my R1 is gonna be, this case gonna be square root 2, right? Because of Pythagoras. Okay. So yeah, so I have B1, my R1 is square root 2 centimeters. And I plug that in. So B1 is going to be mu naught I 2 pi R. My R is going to be square root 2. And then I have to times cosine 45 degree. So cosine 45 degree is 1 over square root 2, right? And I plug in the numbers. And then I get, in the end, I get 2. Yeah, I get this 2 times 2 divided by 2. So it's 2 to the 10 to negative 4 Tesla to the right. So I'm gonna say plus x direction. So that's my answer for point A. And if you do the same thing for point C, you're gonna get the same number but to the right direction. Yeah, so this is gonna be my magnetic field at point C. If that makes sense, can you click the like button? Yeah, and please try other questions on this problem set. Yeah, you have number 4 is about line integral of B along a path. Yeah, and number 6 is about the force on a moving charge due to magnetic field. Number 7 is about the net force on each wire. Yeah, and the field when you involve some kind of line, a combination of line and circular arc. Same as 9, and so on. Number 11 is about toroid. Yeah, to find the field inside the toroid. You're going to use some kind of Ampere's law. 12, you're going to use Ampere's law. Also, you have coaxial cable. Yeah, with the wire in the middle with some current. And the outside will have another current in opposite direction. So what is the magnetic field inside this coaxial cable? Or let's say you have a sheet of charge. Okay, so that's the problem for magnetic field. Okay, so maybe I give to close this class, I send you back to the breakout room again, and you can chat with your friends to reflect on the class today. How do you feel about the class today? What's challenging for you? What do you need to review? Yeah, if there's anything confusing? Okay, let me recreate. Maybe I make it more people so you can talk in 4 or 5 people. Okay, so 5 minutes. Take some time to reflect on today's class, what you can remember, what you need to review. Okay, and if you're ready, please come back and type any comments for me. I will be around for about 5 more minutes. Okay, so 3 minutes to reflect for today. You have any questions? Okay. Okay, so yeah, thank you for joining class today. I will be around for a couple minutes if you have any questions. Yeah, otherwise, enjoy the rest of your day.
Thank you, sir.
You're welcome.
Thank you, sir.
See you next week.